good thing about chapter 19, well, I think even though there are a lot of reactions, a lot of what you have to memorize just has to do with the functional groups. This is really the chapter of functional groups. I think I've said this to all of you already, so I apologize for sounding like a broken record. If you haven't already, I would definitely recommend making a cheat sheet with all of these functional groups, any naming rules, pictures of the functional groups so you know how to identify them. That will be something that you're going to be tested on this semester. All right. So, our carboxylic acid group. This right now is the most oxidized functional group that you're probably going to deal with, which means it's always going to have first priority in names. So for example, if we had something like this, I'm not going to necessarily make you name this because you wouldn't put an aldehyde and a carboxylic acid group in the same one. But in terms of numbering, okay, which way would you want to number? Would you want to start numbering from left to right or from right to left?
Right to left.
Right to left. So that's what it means by first priority. So even if you had, you know, an alcohol group or a halogen, you're always going to start the numbering from the carbon that has the carboxylic acid group. If we just take this off, how would we name this carboxylic acid? Butynoic acid. So 4 carbons, but, all single bonds, ane, drop the E, add oic acid. Why not 1 butanoic acid?
It's redundant.
It's redundant, okay? The carboxylic acid group is always going to be terminal, so it's always going to be on the first carbon, so don't worry about identifying what carbon that one's on. What is the common name of this guy?
Yes.
Close?
Acetic.
Acetic acid. Acetic acid, this is really the only one that you have to worry about knowing the common name for because it is used so much in industry. If I asked for the IUPAC name, what would it be?
Ethanoic.
Good. Even though you won't have to know the common names, I find that it is helpful to know the first 4 prefixes. So we know acete is 2 carbons. Do you guys know the other 3? Form is for 1, so formic acid would be 1 carbon carboxylic acid. 3?
Propion.
Yeah, very close, yeah. Very
Spelled all weird.
propion.
Yeah.
Very close to prop. And what about 4?
Butyr.
Butyr, good. Okay, you'll notice again the naming of like the endings are slightly different. For common names you would just add IC. Again, I don't think you need to worry about that for your other prefixes, but just keep in mind it's not acetoic acid, it's acetic acid. Pretty easy to remember. Any questions about naming? Feeling okay with naming? Would these bonds be considered polar or non-polar?
Polar.
Polar, good. If I wanted to, what number of carbons are soluble in water?
1 to 4.
1 to 4. So if you have pentanoic acid, you should know that that one is not soluble in water, okay? That is something that you'll be asked. What is the orbital hybridization of this carbon?
SP2?
Question mark?
Question mark?
It is sp2,
Okay.
okay? So again, looking at attachments, so we would have 1 attachment here, 2, 3. So spp, sp2. What about this oxygen? What's the orbital hybridization of that oxygen?
It's an sp2.
It is also sp2. So the key with oxygen, you have to know that there are always two pairs of electrons, hidden in a sense, which count as attachments. So here we have 1, 2, 3, spp, sp2 as well. Chances are you probably won't be asked about oxygen, but it is up for grabs, so I would know that. How about the geometry? So it's sp2, which means what type of geometry? Trigonal, second word. Trigonal planar. Okay. What type of intermolecular attraction can carboxylic acids have?
Dipole.
Okay, and
Hydrogen bond.
the specific type would be hydrogen bond, yes. So this is hydrogen bond capable. And we know that how? By looking at it, how do we know that this can make hydrogen bonds?
Because there's an open bond. I don't know.
That's okay.
Take it back.
Oh, is it because the hydrogen and the oxygen can make bonds with other water or hydrogen?
So-
molecules?
It does have to do with this alcohol group, or the hydroxyl group. To have hydrogen bonds, you need to have a hydrogen with either a nitrogen, an oxygen, or a fluorine, okay? So here, because of the greater electronegativity, the bigger difference, we know that we are gonna get some charges, and these charges can interact with other hydrogen bond capable molecules, okay? So what does this mean about relative boiling points? Are they going to have higher boiling points? Are they going to have lower boiling points? Higher, good. Okay. The key with this, they actually can make two hydrogen bonds. Okay, so we have our carboxylic acid group here. We know the charges tend to run like this. So we have two hydrogen bonds from the same molecule, okay? Just for a reference point, water can have 4 hydrogen bonds, okay? So the 2 hydrogen bonds mean that this has a very high relative boiling point, higher than alcohols even, and we know that alcohols have a really high boiling point as well, okay? How are we feeling about the physical properties? Pretty good? If we had a carboxylic acid running in an NMR, would the hydrogens and carbons be shielded or de-shielded? De-shielded, which means they would show up downfield or upfield.
Down.
Very good. Okay, so carboxylic acids can act like an acid and a base. If a carboxylic acid is acting like an acid, does it become protonated or deprotonated? Deprotonated, good. So we end up with something like this, okay? And we see 2 different structures, okay? What force stabilizes these 2 structures? Resonance, good. So we can see the charge is being delocalized, meaning that the electrons are moving, meaning that resonance is responsible for this. Let's see. Okay. So there is a particular type of phenomena where adding electronegative groups to an acid makes it more acidic. What is the term for that? The inductive effect. So remember, there are technically two kind of parts to this. You have the number of electronegative groups. So one group, well, having 3 electronegative groups is going to make something more acidic than just having 1 or none. What's the second piece? What else affects the acidity?
How far it is from the carboxylic
Good.
group.
So the number and the distance. If the electronegative groups are added right next to the carboxylic acid group, you're going to see an increase in acidity or an increase in the strength of that acid. Just a quick reminder, when we're talking about pKa, okay, what's the relationship between pKa and acidity?
Increase pKa, decrease acidity.
Good, so it's inverse. So the lower the pKa, the stronger the acid. Okay. So again, these carboxylic acids can act like both an acid and a base. You should know that they're relatively strong acids, not strong acids, but relatively strong. And they're considered weak bases. They're not strong bases at all, which makes sense from their name. So if acids become deprotonated, bases become protonated. Where is the protonation going to happen? Is it going to happen on the hydroxyl group or on the carbonyl group? What was that, Amber?
The carbonyl.
It's actually on the hydroxyl group, and let's see why. Wait, no, I said that wrong. Sorry, you said it right. You said it right. I'm sorry.
Okay.
I know it's Tuesday, but happy Monday. Okay. Now, why not on the hydroxyl group? It has to do with the fact that this positive charge can be delocalized when it's added to the carbonyl group. It can't, if we were to add the hydrogen here, making this positive, we wouldn't be able to delocalize the charge, okay? So that is why we have the hydrogen added there. We can delocalize the charge here, so the charge can move to the carbon. This, or to this lower oxygen. Okay, so because we can move this positive charge, we can delocalize that charge. It does make it more stable. Still stabilized by resonance because we have that charge being delocalized.
So delocalization of the positive charge just means it can be on either the carbon or the oxygen.
Yeah, and either oxygens, not just one oxygen, right? Because this oxygen is technically different from this oxygen.
So it can be on 3 different places.
Yes,
Okay.
So it's just a movement of
the positive
charge.
charge. Yep.
But isn't there a positive charge on both hydrogens too?
So with this one, because we have the addition here, the charge of the bond isn't going to be the same as what you would expect here. So by protonating it, it does throw off a little bit of the dipole-dipole.
Okay.
Okay. So, in terms of what you need to know, I would definitely know that resonance is involved in stabilizing the intermediate, whether you're talking about it acting as an acid or a base. You should definitely know what's being protonated or deprotonated and where. I don't think you need to worry about drawing these things, but you should know, like I said, the carbonyl group is protonated, not the hydroxyl group. Well, like Amber said actually, but definitely know the inductive effect and know what it means. But in terms of drawing, don't worry too much about drawing. I don't think that's going to be a focus.
So when it's acting as an acid, it's protonated at the same place?
It's deprotonated.
Or, oh yeah.
It's deprotonated on the hydroxyl group.
Okay.
So protonated on the carbonyl group, deprotonated on the hydroxyl group.
Okay.
Any other questions about acting like an acid or a base?
The lower the pKa, the higher the acid.
Yes, stronger the acid, higher the acidity, either way you want to say that.
Lower pH.
Lower pKa. Oh, sorry. Oh, you're saying it would lower the
pH.
pH of the solution. Yes, yes.
Deprotonated on what?
The hydroxyl group. So this is where the proton is pulled off. This is where the proton's added. All good questions.
Now, does resonance stabilize the base as well? Like
Yes.
it does? Okay.
Yep, because we have that charge being delocalized. Okay, it can look either way here, so we can have, the electrons are moving, the charge is shifting, so resonance is stabilizing that.
Oh, no, I mean in the base with.
Oh, sorry, base with a positive charge, yes.
Yeah, it
Yep,
does that too. Okay.
same for both.
Awesome.
So addition, elimination is kind of a general reaction mechanism that you should know. So essentially we're running two different reactions. We run the addition first and then we eliminate, okay? So you should know what's generally happening in either of these. Again, I'll draw everything out. I don't think you necessarily have to worry about drawing, but you should know what's happening at each point in the reaction. Okay, so the L here is just denoting our leaving group. So we have our carboxylic acid, and we're reacting it with a nucleophile, okay? So thinking back to our carbonyl group, when we're looking at the carbon and the oxygen here, where is the negative point of this dipole going to be?
Yeah, oxygen.
Okay. And we're reacting with the nucleophile. The nucleophile is what we're trying to substitute for our leaving group. So what charge does the nucleophile have?
Positive.
Negative.
Negative. So it likes positive things, which
Oh.
means it has to be negative. I know. So negative, meaning the hydrogen's going to be positive. So just by looking at these charges, you should see where the reaction's kind of going to be taking place. The negative nucleophile is going to target the positive carbon. Hydrogen is going to be attracted to that negative oxygen. So our intermediate in this addition reaction, and another side note, every addition reaction involves the breaking of a pi bond and adding something to the two adjacent atoms. So obviously we're going to be breaking this double bond here. Okay, and our hydrogen is added here. So we went from trigonoplanar to, what's the geometry of this intermediate?
Tetrahedral.
Tetrahedral. And the orbital hybridization of that carbon is sp3. What about this oxygen?
sp3.
Also sp3, good. Okay, so that's the addition reaction. We broke the pi bond in the carbonyl group, we added the nucleophile to the carbon, and the hydrogen to the oxygen, okay? This second piece is elimination. From last semester, you should remember in elimination, we removed something from two adjacent, what's the word I'm looking for? From two adjacent atoms, and that forces a double bond to form. So, we are going to be removing our leaving group, and this hydrogen is going to come off again, okay? So, that's going to force the double bond to reform between the carbon and the oxygen. So we still have our R group, we reform our carbonyl group, and we're left without a nucleophile.
So there was really no point in adding the hydrogen, but it was only added because the nucleophile has to be attached to a hydrogen.
Right, so when we do break this bond, we have to add something to that oxygen to make it stable. It wouldn't be stable as just an O with a negative, okay? So yes, it does seem redundant to add it just to take it away, but it's kind of a means to an end to get our nucleophile here. I know he made a big deal about alcohols not being good leaving groups, and that kind of goes back to this intermediate here. You know, why is the leaving group the one that leaves? So if you think back to, I think it was chapter 8 maybe, for this to be a good leaving group, we actually have to protonate it. We have to make it hydroxonium ion, okay? So if the OH isn't going to leave the, it's pretty difficult to break carbon-carbon bonds, so that wouldn't really readily happen. And our nucleophile just attacked the carbon, so that's why the leaving group, no matter what it is, it's probably going to be a better leaving group than the hydroxyl group. I know he made a big deal about that in class.
Where is because it's of the carboxylic acid, but where's the hydroxyl group that
So-
makes it the carboxylic acid?
I see what you're saying. So this is more of talking about, I think, the derivatives of carboxylic acids.
Because wouldn't that just be an aldehyde or a ketone then?
It would depend on, that's most likely not a carbon group and not a hydrogen, so it's probably a carboxylic acid derivative, so one of the ones that we talked about. So it could be,
Acid halide.
yeah, something along those lines. So I know what you're saying. It's not really necessarily a carboxylic acid, but it is some type of derivative. And we know that our halogens, particularly iodide, are good leaving groups. So it is most likely an acyl halide, but it could be other derivatives as well.
So pretty much just in addition-elimination reactions, it's the derivatives that are going to be reacting.
Right, because you, like I said, just barely the hydroxyl group wouldn't be a good leaving group. So
Okay.
yeah, running it on a carboxylic acid wouldn't probably go very well.
Yeah.
Okay. So again, in terms of knowing what's going on here, I think you should know the geometry. So trigonoplanar, tetrahedral, trigonoplanar, along with that the orbital hybridization. I would know what generally is happening in addition and elimination because he could just talk to you about like maybe a word problem and he's asking, for example, so in an addition reaction of an acyl halide, where does the nucleophilic attack occur? So you would say on the carbonyl carbon. So if you know what's generally happening here, I don't think it's going to be drawing it, I think it's going to be interpreting his questions based off of what you know about this reaction.
And for like orbital hybridization, all the ones we've looked at, it's been like the carbon and the oxygen have been the same. Is that always the case?
No.
Or, okay.
No. So yeah, I'd be careful of that.
That easy.
And also, like if we look here, for example, what's the orbital hybridization of this oxygen?
Oh, sp3.
So you can't assume that it's going to match, it just happens to be the carbonyl group. If anything happens to the carbonyl group, that is going to match, but I wouldn't want you to assume that's a rule. Okay. So into all of the derivatives. So Amber, you mentioned acyl halides, okay? So acyl halides, you have your carbonyl group with a halogen attached. In terms of naming them, it's really just acyl halogen. So if I had a chlorine here, it would be acyl chloride. Okay. There are two types of reactants that are specifically talked about. I don't know if they're going to be a focus in terms of questions. But for example, thionyl chloride is used to make acyl chloride, or phosphorus tribromide can make acyl bromide. Just keep those in mind. When we react a carboxylic acid and an acyl chloride or an acyl halide, we get this. Anybody remember what this is?
Anhydride.
Anhydride. You guys talked a lot about this in class or in lab, right?
Mm-hmm.
You also talked about naming anhydrides.
Yeah, I don't remember.
So it's really not as intimidating as it looks. And again, this is more of common naming, not what's the word I'm looking for? Not IUPAC naming. So for example, in class, I think you used maleic acid to make an anhydride.
Yeah, in lab, yeah.
Okay. So whatever acid you use, you replace the acid with anhydride. So maleic acid becomes maleic anhydride. He could give you any type of crazy acid name. All you would have to do is remove acid and replace it with anhydride. I'm pretty sure he's done that before. Just giving you something that you've never heard of. So don't overthink it, just replace acid with anhydride.
So to make an anhydride, you use any of the acyl or
They use acyl chloride.
acyl. I can't pronounce it.
They, in the example, it's acyl chloride. I have a feeling it probably can't use fluorine because it's not a great leaving group.
Mm-hmm.
Other than that, I'm not sure. You could probably use iodide because it is a good leaving group, but I don't know how easy it is to make acyl iodide. That might be the hard part, you know what I mean? Yeah. But if you have acyl iodide, that might be, able to use. I would just know it as acyl halide, but if he does say acyl chloride, just don't get confused by that. Okay. If we wanted to make a cyclic anhydride, does anybody remember the starting product that we would need?
Dioic acid.
Dioic acid. Why a dioic acid?
It has two hydrogen bonds?
Not two
Four
hydrogen,
bonds.
two carboxylic acid groups, right?
Yeah.
That's the key part, okay? So we know to make our anhydride, we had to have a carboxylic acid, and we had an acyl chloride, so we had some type of carbonyl group. So one of these came from the carboxylic acid, the other one came from the acyl chloride. So if we want an intramolecular reaction to take place where we have a ring closing, we need both functional groups on the same reactant. So a dioic acid can be heated to create a cyclic anhydride. If we're talking about stability, what two, like, how do I want to put it? So in terms of like ring size, what are the two most stable sizes?
5 and 6.
5 and 6. So this is a 5-membered ring. A 6-membered ring would also be extremely stable. How do we feel about anhydrides? Cyclic and straight chained.
I might be asking an overcomplicated question.
That's okay.
When you're heating it, I see that you're removing the 2 hydrogens on the hydroxyl groups to create that cyclic structure, but
So it's not just the hydrogen. So let's take a quick look, because that is a good question. And it's not an overcomplicated question. So basically, we have this, right? They drew it nicely for us, so we can see where the reaction's taking place. So we're not just removing the hydrogens, right? We also have to remove an entire hydroxyl group. So we remove a hydrogen from one and a hydroxyl group from another.
Gotcha.
We're actually removing water. So that makes sense why heat is necessary, right? We're dehydrating it. That's really all that's going on. That's a great question.
I feel like that's how he'd word it on the test.
Yeah.
So he'd be like, what
Right,
do you make when you dehydrate? Dioic acid.
exactly. Yeah, that's a
I
good
think
way
it's
of
just the
putting it.
heat that threw me off. I'm like, let's see what's going on.
Yes. So good, good. Any other questions? Are we feeling okay? All right, let's move on to esters. Okay. So you guys may remember esterification.
Barely.
I don't think he actually used that term in class, but that's really all you're talking about here, the preparation of esters. So it is a carboxylic acid derivative. Does anybody remember what else it reacts with to make an ester? An alcohol. Okay. So, and when we're talking about functional groups here, so we have our carbonyl group, we have our oxygen, but on the other side, instead of a hydrogen, we have another R group, okay? And I'm actually going to redraw this so we can see where the reaction's taking place. So again, we're going to remove the hydrogen from the carboxylic acid. We're going to remove this OH group. So again, water is another product of this reaction. And we're, yep,
Sorry.
no, it's okay.
If you're using H2SO4 as the catalyst, is that what you're using for that?
It doesn't specify here. It does say in, you know,
Or is that for a cyclic one?
for cyclic.
Oh, okay.
Either way. That's okay though. So ester, definitely be able to pick this one out. I think it's discussed more in chapter 20, as well as naming esters, which we can get into if we have time. Okay. So if we're talking about cyclic esters, very similar to dioic acid, we know we have to have a carboxylic acid group and a hydroxyl group on the same compound. This is referred to as a hydroxy acid, which kind of makes sense. Okay, so our hydroxyl group, our carboxylic acid group, I'm not going to draw all the hydrogens out. So this is one where you do use an acid for this. I think that's just to help with deprotonating this and removing the hydroxyl group, because that has to happen for the oxygen to bond with that carbon. So this oxygen is going to react with this carbon. We're again going to remove this hydrogen, this hydroxyl group, and our final product. So we still have our ester group, but it's been made into a cyclic compound. What's the term for a cyclic ester?
Lactone.
Lactone. Again, 5 and 6 membered rings are ideal. Again, I don't think it's going to be a focus, but just to keep in mind. So here we see it's a 6-membered ring. But if you look back at our starting product, 1, 2, 3, 4, 5, there's only 5 carbons because the oxygen is one of the members of that ring. So if he gives you a hydroxy acid and says, would this form a lactone, you need to know that this is going to also be a member. Okay, so if there's 4 carbons and an oxygen, that would work, or like we see here, 5 carbons and an oxygen. Again, I don't think that's going to be something he focuses on, but just so you're prepared. Okay, all set with esters and lactones. Gonna erase some of this. Who remembers amines from general chemistry?
Kind of.
I remember more from last chapter.
So, amines are technically not carboxylic acid derivatives, but they're discussed in this chapter, so I want to make sure you guys remember these. So amines are derivatives of ammonia, which is just NH3. So essentially we're taking one of those hydrogens and we're replacing it with a carbon group. So you can have just one R group added. You can have 2 R groups added or 3 R groups added. And these are classified as primary, secondary, and tertiary. So if we take a carboxylic acid and we react it with an amine, this one was a primary as an example.
Is that what the apostrophe means?
Yeah, it's just so you don't get it confused with this R group, so you can see at the end what's being added where. So if we react these two, essentially what's going to happen, we're going to remove one of these hydrogens, and we're going to remove our hydroxyl group, and the nitrogen is going to bond to this carbon. Okay, so we see our one less hydrogen here. So technically we could also do this with a secondary amine. We would not be able to do it with a tertiary amine because there wouldn't be any hydrogens to remove. But again, water is also another byproduct here. So carboxylic acid, amine, this one is referred to as an amide. So when you have the nitrogen bonded directly to the carbonyl group, that's considered an amide instead of an amine.
Do we need to know how to name them?
No. Even with amines, you don't really, from what I remember. I think you do, some general chemistry classes review it, but I don't think many do. And I don't remember that being a focus for this class. Okay. So amines, amides. There is another. We also talked about enamines and amides. I think that's the one. Those are the ones we talked about last time. So an amide. Think anhydride. Okay. So just get rid of this for a second. We have our carbonyl group, we have our other carbonyl group. Instead of an oxygen in the middle, we have a nitrogen. So it's essentially an anhydride with a nitrogen replacing that middle oxygen. And you actually make amides by using the same process as making anhydrides. So who remembers the starting product?
Dioic acid.
Dioic acid. So you're still heating it. The only difference, you're doing it in the presence of ammonia. So this is where the nitrogen comes from. It's in the presence of ammonia. But the same process is occurring. Nothing else is changing. And this would make a cyclic amide. But this is just the general functional group of an amide.
Is it always ammonia or it can be any amine?
I guess it would be any amine. Dr. Cosper's example specifically has ammonia, but then it says in the description amines. So you could react it with amines, as long as there's nitrogen readily available. Okay? So, stepping back to amides. Similarly to esters, we can make cyclic amides. What was the starting product for a lactone?
The hydroxy acid.
Good. So this is very similar. Instead of a hydroxyl group, we're going to have an amine on the end. So let's see here. 1, 2, 3, 4. Okay, so we have our amine on one end, our carboxylic acid on the other. Same thing is going to happen. This O, oh sorry, not the O. The carbon in this case is going to react with our nitrogen. We are going to remove one hydrogen here. We're going to remove our hydroxyl group. Okay, so we still have our amide functional group, it's just in a cyclic compound. Cyclic amides are referred to as lactams. The way I remember the difference, lactams, cyclic amide, both have M's. Okay. So, brief overview, because the last two reactions aren't actually involving derivatives or new functional groups. So we have acyl chlorides, acyl halides, anhydrides, cyclic anhydrides, esters, lactones, amines, amides, amides, lactams. You can see where the need of putting all this information into a nice handy sheet would make things a lot better. And you are going to learn more about esters and naming. Right now, I think all you need to know is what an ester is and how it's formed, but eventually you will need to be able to name them.
What'd you say that starting product was for that? The cyclic amide?
So it doesn't have, I don't know the name. So this is just saying amino acids can be used because amino acids have an amine group and a carboxylic acid. I don't think there's a general class of functions that have a carboxylic acid and amine. The last two reactions discussed, so we have reduction of carboxylic acids, and we have Ballard Zielinski reaction. So, when we're talking about reducing a carboxylic acid fully, okay, who remembers the final product that we're expecting? Primary alcohol. Okay, this should be review from last semester. Essentially, you're reducing it to its most reduced state. And keep in mind, you can go back and forth from a carboxylic acid to a primary alcohol. For this one, I would know the reducing agent. So it's lithium, aluminum hydride. This is considered a strong reducing agent, okay? Which is why we can fully reduce that carboxylic acid. He might not even mention that it's a reduction. He might say a carboxylic acid has lithium aluminum hydride added to it. What would you expect the final product to be? So you don't know that necessarily a reduction is taking place. So you really should link this as a reducing agent. It's pretty popular. It's also discussed in chapter 20, I believe.
Will we ask about sodium borohydride? Which is the other reducing agent?
Yeah, I think that one, I haven't seen it mentioned in chapter 19 or chapter 20, so I don't think that you would have to worry about it. He might also just say a strong reducing agent. Okay, that's another way that he could word it. Okay. So this reaction really you're just running a bromination. The only difference between this reaction and the other ones is you're actually not reacting on the carboxylic acid, you're reacting on the alpha carbon. Hello. Hey, you might need to grab another chair. Okay, so again, if this is our carboxylic acid group, this would be our alpha carbon. So we're going to react with bromine. And the bromine is going to be added there. So Hellweiler-Zielinski, bromination of the alpha carbon. Any questions about those last two reactions?
Is it only gonna be one bromine every time?
I think you might have asked me that one before. I haven't seen anything indicating that there would be additional brominations. I haven't read that section of the book yet though, so I don't know if the book mentions it or not.
But you could like get rid of the second hydrogen and put another bromine on that. No.
That could be possible, but we also know that sometimes multiple halogenations are inhibited, right?
Yeah.
So I'm not 100% sure. I'd have to review the chapter to make sure. I think if that was possible, there would be some mention of it, but
Yeah.
I can't say for sure.
So Hellweiler-Zielinski reaction is just adding the bromine to that alpha carbon.
Yep.
And that's it.
That's it. How do we feel about chapter 19? Super good.
Overwhelmed.
Overwhelmed. Like I said, I keep saying it, but creating a cheat sheet for your functional groups will save you in the end. Even if he doesn't, ask you a lot of questions on this quiz, I would expect seeing a lot of questions on your midterm. So if you do it now, it's gonna save you a lot of headache later on.
Can we go back to inductive effect?
Yes, absolutely.
Tomorrow's chapter 19 quiz.
Yeah. So, inductive effect. So you should remember that there's two pieces to this. We have, the number of electronegative groups present, and the distance between those groups and the carboxylic acid group. So let's take a look at some examples. So, if we have this, okay, so we have three different carboxylic acids. This first one has no electronegative groups present. Here we have 2, here we have 3. If we give their pKa's, this first one is 4.76, 1.26, 0.63. So we see a really dramatic decrease in pKa, okay? And we talked about the fact that pKa and acidity or strength is inversely related. So the lower the pKa, the stronger the acid. So this would be considered the strongest acid in this group because it has the most electronegative groups. So that's the first part. The number of electronegative groups. The more groups you have, the more acidic, the stronger, or the lower the pK. Either way you think about that. Okay, if we had... No. actually. So again, 3 different acids. This one we see no electronegative groups. Here we have the electronegative group right next to the carboxylic acid, and here it's all the way on the end. Again, pKa 4.82, 2.84, and 4.52. So we can see that by adding the halogen right next to the carboxylic acid group, we cut the pKa in about half. But when we put it all the way to the end, we see that the pKa jumps back almost to where it was without any electronegative groups present. So the greater the distance, the less acidic the acid becomes. So the inductive effect has 2 parts. The number of electronegative groups present. The more groups there are, the more acidic that acid is, or the stronger that acid is. The second piece is the distance from that group and the carboxylic acid. The greater the distance, the lower the pKa, or the weaker the acid. Does that help with the inductive effect? Any questions about that?
So the more distance, higher pKa, less acidic.
I have a feeling that he's going to describe the inductive effect to you, and he's going to expect that you know what he's talking about, right? So expect to fill in the blank here. I don't think you need to know relative pKa or anything like that, but he could give you an example. He could give you something like this and say, indicate which is the stronger acid.
His go-to.
It could be.
I have class.
Yeah, no problem. Good luck
You can sit
tomorrow.
here if you want. Thank you.
So again, I don't think you should expect too many questions.
Alright.
Thanks. I think my only question really is that he asks a lot of questions where it's like, oh, if I doubled this or doubled that, like, would it go faster or would it go slower? I
Almost
never
certainly
know
every
the answer.
time.
I know,
So-
the same.
I guess, in 50% chance of it.
I do too.
Like, I
always get it
know
wrong.
what should happen, but just the way it's worded, I get so confused.
And it's difficult because it's really dependent on the mechanism, and he doesn't always tell you the mechanism outright.
Yeah.
I mean, the good thing about this chapter is we don't really have any mention of, it's really chapter 6 and 7, so those are going to carry throughout, right? So understanding those mechanisms can really tell you whether doubling something is going to affect the reaction rate or not. You really don't have that in this chapter. So in terms of, just for future reference really, you need to know the type of mechanism that's going on. So when we're thinking back, so we have SN2, SN1, E2, E1. So the unimolecular reactions are the ones that typically trip people up, because when we think of reactions, okay, we know that things are colliding to make the reactions happen. So if you add more of one, it makes sense that the reaction rate should increase. But with unimolecular reactions, we're only looking at the alkyl halide, or it could be an alkyloxonium ion, anything other than the nucleophile. So if we know what the nucleophile is, and he's talking to you about changing the concentration of that nucleophile, you should know that that's not going to affect the reaction rate, because the reaction rate is dependent on whatever has the leaving group. So that can be kind of difficult. Trying to think. So again, not necessarily for this chapter, but when we talked about alkyl-oxonium ions. Just to have something other than alkyl halide. Okay, this is considered an okay leaving group, so whatever we're reacting with, it wouldn't matter as long as we had, if you change the concentration of this, that would impact the reaction rate, but changing the nucleophile wouldn't change it. With bimolecular, if you're changing the concentration of either reactant, it's going to affect the reaction rate. I wish, has he asked any questions like that this semester yet?
I
On the
have
last
the actual
quiz, yeah.
question
Okay.
right here. It's question 15 if you want to read it. It's
Sure.
long, so I don't want to just read it out to you.
You said 15?
Yeah, it's the top one.
You do a bromination of a ketone under acidic conditions. This reaction is dependent on enolization. If you double the ketone concentration, what will happen? Okay.
I think what threw me off the most is all that I really remembered about the bromination in acidic conditions, that it's only one alpha hydrogen replaced,
Right.
where in basic conditions, it's all of them, all the...
Right, there's really no mention of the mechanism of the reaction.
Which threw me off. I guessed, 100% guessed, and I got it right, thankfully,
Right.
but
Yeah. So,
I had no rhyme or reason why.
okay. So, because this isn't an SN1 or an E1 reaction, okay, we can assume that the concentrations of both of these are going to affect the reaction rate, okay? So he said that you doubled the amount.
Of ketone. Yeah, if you double the ketone, what will happen to the reaction rate?
Right. So it's directly related in this case. Again, because it's not, we're not talking about an SN1 or an E1 reaction. So doubling either of these, and this was also an excess. So basically the reason he put that is this isn't going to limit it in any way, right? So it could get tricky, but I don't think he would give you that because you wouldn't be able to know. So if the bromine was your limiting reagent and you doubled this, essentially that means that the bromine is still going to limit how fast or how much of the reaction can take place. But because this is an excess and you're doubling this, this is what's going to, if the reaction isn't going to be limited by anything. So if it's not an SN1 or an E1 and you're doubling an amount of reactant, you're going to see a doubling of the reaction rate. If you halved a reactant, it would halve the reaction rate. As long as we're not talking about an SN1 or an E1, then you would have to think a little bit more critically about what is being halved or doubled.
Didn't he say it resembled an SN2 reaction? Like in his notes?
Oh, maybe in his notes.
I think he did.
Okay, that could be the case. I was going to say, I don't remember off the top of my head.
Like, oh, makes me mad. One
But-
tiny detail.
But knowing, if you did know that it's an SN2 reaction, you would know that the reactions of both are going to affect the reaction rate. So I know it's,
It doubled.
Okay.
yeah. So it would make sense if it was an SN2 reaction.
Yeah.
And again, yeah. I find that it's easier to make note of the ones that are SN1 or E1s, if he mentions those, because those are the ones you have to be more careful of. It's a good question. I know those are tough, but it's really just remember, if you can remember the mechanism, and then thinking critically about what is actually being affected. Those are tough though. I can go into chapter 20 if you guys don't have any questions about chapter 19. I don't know what you guys, with the quiz tomorrow, I don't know if it would confuse you to go over chapter 20.
I think it would me personally.
That's totally fine. I was gonna say, Amber, I don't know if you wanted to hang out, but if it's just you and I, Jazz, we can just go through chapter 19 since that's what the quiz is on.
I was here last week, so.
Oh, so you're feeling,
Yeah.
okay, alright. So we can end it. Sure. Okay. How did lab go, Jazz?